Today, we're going to get into the story of motion itself. So, what if I told you that physics, it's not really about memorizing a bunch of formulas? What if it's actually a language? A language that lets us predict the future. Seriously, it lets us look at something, see where it is right now, and know exactly where it's going to be next. Okay, so to predict the future like that, we first have to learn how to read the story of motion. And, like any good story, it's got its own language, its own main characters, and we're about to meet them.
But how do you even do that? How do you translate something like, I don't know, a car driving down the street or a ball flying through the air into something you can actually analyze? Well, the answer is way simpler than you might think. We just turn it into a picture.
All right, so the very first word we need to learn in this new language is displacement. Now, this isn't just about how far you've gone. It's about where you end up. I mean, think about it, right? Taking 10 steps forward is a completely different story from taking 10 steps back. That's displacement.
And this is where the story really starts to take shape on a graph. If we plot an object's displacement over time, a totally flat, horizontal line tells the simplest story possible. Time is ticking by, but the object, it's not going anywhere. It's standing perfectly still.
Okay, but what if the line is straight, but it's sloped? That's when our object is on the move. It's covering the exact same amount of ground in each tick of the clock. That means it's moving at a constant speed, a constant velocity. And get this, the steeper that slope is, the faster it's going. It's such a simple but really powerful way to see motion.
But let's be real for a second. Stories where nothing changes are kind of boring, right?
The real drama, the good stuff, happens when things speed up or slow down. And in the story of motion, that big plot twist has a name: acceleration. So here we've got the two main kinds of plot twists you'll see. Over on the left, that's uniform acceleration. Just picture a car steadily speeding up on the highway, right? Its velocity changes at a nice constant rate, giving us that clean, straight, sloped line. But then on the right, that's non-uniform acceleration. This is more like a car in stop-and-go city traffic. The velocity is all over the place, changing unpredictably, and that creates this kind of chaotic, curved line. Okay, let's actually put this to the test. Imagine a car starting from a dead stop. It starts accelerating nice and steady at 3 meters per second every single second. Well, using what we just learned, we can literally predict its future. We know that after exactly 8 seconds, it's going to be going 24 meters per second. And we also know it will have traveled precisely 96 meters. See? That's the predictive power of physics right there. All right, so we've got the basics down. Now let's try to read a more complex story. It's one you've definitely seen play out 1,000 times. The tale of a simple bouncing ball. It seems so simple, but the story of a bouncing ball is actually this amazing little drama. It starts from rest, zero velocity. Then, boom, gravity takes over and pulls it down faster and faster. When it hits the ground, you get this sudden, dramatic plot twist. It completely reverses direction. It springs back up, but it loses a little energy in the bounce, so it never quite makes it back to where it started. And this whole cycle just repeats, each bounce a little smaller than the one before until it finally just stops. And here's the really cool part. We can watch this one bounce from 3 totally different angles. We've got the displacement graph, which shows its height, the rise and fall. Then there's the velocity graph, which tells us about its speed and when it changes direction. And finally, the acceleration graph, which shows that constant, steady pull of gravity. It's 3 different views, 3 different graphs, but all telling one complete story. Okay, so far, everything we've talked about, it's all been in a straight line, right? Up and down or back and forth. But the real world isn't one-dimensional. So let's add a new chapter to our story and see what happens when things go up, over, and then down again. And that brings us to a whole new kind of motion. What happens when you don't just drop a ball, but you throw it? Not just up, but forward. How do you read the story of that beautiful, curved, arching path it makes? Well, that's what we call projectile motion. And for now, we're going to make a pretty important assumption, just to keep things simple. We're going to pretend that the only thing acting on our object is gravity's constant downward pull. So for the moment, we're totally ignoring air resistance just so we can see the pure physics at work. And here is the absolute secret to understanding projectile motion. You take that one complex curved path and you split it into 2 separate, way simpler stories. First, there's the horizontal story. That's just a simple tale of constant speed, nothing pushing or pulling it side to side.
Then there's the vertical story, which we already know. It's that same old tale of constant acceleration thanks to gravity. These two stories happen at the exact same time, and when you put them together, you get that beautiful, perfect arc.
So check this out. If we launch a ball at 20 meters per second at a 30-degree angle, we can predict its entire journey. We can figure out exactly how long it's going to be in the air. The physics tells us its total time of flight will be just a little over 2 seconds. 2.04 seconds, to be exact. And we can predict more than just how long it's in the air. We can also nail down the highest point of its journey, its apex. At the very peak of that curve, that same ball will have reached a maximum height of 5.1 meters. That is the power you get from understanding those two simple, separate motions. It's the kind of power that lets athletes and engineers predict exactly how things are going to fly. Now, everything we've talked about so far, it's kind of been a fairy tale, right? It's all happening in this perfect physics world where there's no air resistance. But we don't live in a fairy tale. So it's time for our final chapter, where a perfect model slams right into reality. Just take a look at this comparison. On the left, you've got that perfect, beautiful, symmetrical parabola we've been talking about. But on the right, well, that's the messy, lopsided path you get in the real world. Air resistance, or drag, basically acts like the villain in our story. It's always pushing against the object, stealing its energy. It makes the path shorter, it skews it, and it makes the object fall way more steeply than it climbed. And this is where things get really interesting. This whole idea of air resistance leads to a fascinating concept called terminal speed. So imagine something falling from a really, really great height. As it picks up speed, as it goes faster and faster, the upward push from the air resistance gets stronger and stronger too. And eventually, there's a point where that upward push perfectly balances the downward pull of gravity.
Let's break that down for a second. At first, when the object isn't moving very fast, gravity is the clear winner, and the object speeds up. But as its speed increases, that drag force fights back harder and harder, creating this epic tug of war. And then you get to this critical moment where the drag force has grown so much that it's exactly equal to the force of gravity. The tug of war is a draw, the forces are perfectly balanced, the net force is zero, and the object stops accelerating. It's still falling, for sure, but now it's falling at a constant speed. So that leaves us with one final thought to ponder. If an object is falling, but all the forces on it, gravity pulling down, drag pushing up, are perfectly balanced, and it's not accelerating anymore, what does that really tell us about the true nature of motion itself?